Hey guys, welcome back. Our last video was a long one and we did lots of examples in practice drawing Lewis structures or Lewis electron dot diagrams. Today we're going to look at two more things. Assigning formal charges is a helpful little trick that we can do to make sure we have the right Lewis structure in cases where looks like there could be more than one way to do it. The second thing we'll talk about today is resonance, which is a phenomenon that we'll encounter sometimes. So let's start by drawing the Lewis structure for the cyanate polyatomic ion. Remember that step one is to add up all of the valence electrons. Carbon has 4, nitrogen has 5, oxygen has 6, and this polyatomic ion has a -1 charge, which means there is one extra electron thrown into the mix. So our target number is 16. And then the second step is to connect the atoms with single bonds. And remember that the central atom should be the least electronegative. So I'm going to opt to put carbon in the center because I know that both nitrogen and oxygen are very electronegative. So I'm going to put carbon here, and I'm going to connect the oxygen on one end and the nitrogen on the other end. And I've just used 4 of my 16. So 5, 6, 7, 8, 9, 10. Remember, I skipped the central for now. 11, 12, 13, 14, 15, 16. Okay, I just hit my target. Nitrogen has an octet, and oxygen has an octet, but carbon does not. Carbon only has 1, 2, 3, 4. So I'm going to do the trick where I move a non-bonding pair and change it into a shared pair. But I want you to think for just a minute. There's actually more than one way to do this. For instance, I could take this non-bonding pair, change it into a shared pair, and then I could take this non-bonding pair and change it into a shared pair. Oxygen still has an octet. Now carbon has an octet, and nitrogen has an octet. But I could just as well, let me duplicate what I had here, 2, 4, 6, 8, 10, 12, 14, 16. Okay, I could just as well have said, let me move this non-bonding pair here, and let me move this non-bonding pair right there. Nitrogen has an octet, carbon has an octet, oxygen has an octet. Who's to say which of those is better? And oh, by the way, I could also have gone this route. Okay, so here's my 16. Again, acknowledging carbon is lacking an octet, I could have chosen to move that non-bonding pair and this. So those are 3 very different, there's my kitty again. You're gonna have to wait a minute. Okay, so these are 3 very different Lewis diagrams, Lewis structures, structural formulas, whatever you want to call them. So we need a way to figure out which one is right. And in fact, one of these is the correct formula. We have tools that allow us to tell whether a molecule has 2 double bonds or a single and a triple and a single, or if the triple and the single are attached in different places. So we need a way to figure out which of those is right. And the strategy that we're going to use is called assigning formal charges. Now here's how this works. It's a little bit, it's a lot of steps at first until you get really good at it, and then you can zip right through it. Assigning formal charges says, for each atom, start with how many valence electrons it has. Nitrogen, I know from my periodic table, has 5. Now, from that, I'm going to subtract the number of electrons in the drawing that are assigned to the nitrogen. So clearly 1, 2, 3, 4, but in this bond, which is a shared pair, one of those is assigned to nitrogen, so that would be 5. And likewise in this bond, which is a shared pair, 1 in the pair is assigned to nitrogen. So that was 1, 2, 3, 4, 5, and 6. Okay, that difference is -1. That's the formal charge assignment for nitrogen. Okay, carbon. 4 valence electrons according to the periodic table, and subtract how many electrons are assigned in this picture? 1 from each of the bonds. So that's a formal charge of 0. Oxygen. Periodic table tells me oxygens have 6 valence electrons. Now subtract 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. Okay, let's see how formal charges for this one compare. Nitrogen has 5 valence electrons. In this picture, 1, 2, 3, 4, 5 are assigned to it. 0. Carbon has 4 valence electrons. In this picture, 1, 2, 3, 4 are assigned to it. Formal charge 0. And the oxygen has 6 valence electrons, and in this drawing, 1, 2, 3, 4, 5, 6, and 7. Formal charge of -1. All right, lastly, nitrogen, 5 valence electrons, and in this drawing, 1, 2, 3, 4, 5, 6, 7 are assigned to it. Formal charge -2. Carbon, 4 valence electrons, and 1, 2, 3, 4 are assigned here. 0. Oxygen, 6 valence electrons, subtract the 1, 2, 3, 4, 5 for +1. Okay, so we've assigned formal charges for each atom in the 3 different versions. Now, here's what we're looking for. First of all, you want as many zeros for formal charges as possible. So right away, this structure, which only has 1 formal charge of 0, I can tell is not the right one. So now I'm down to these 2, and it kind of looks like a toss-up. They both have 2 zeros and a -1. 2 zeros and a -1. So here's how you tell the difference between these 2. The right, or the correct, the accurate Lewis structure. If there is a negative formal charge, it should be on the most electronegative atom. In this picture, the negative formal charge is on nitrogen. In this picture, the negative formal charge is on oxygen. And if you'll remember, oxygen is more electronegative than nitrogen. So that tells me this is the winner. Oops, I cut off those guys. So this structural formula is the right one, and that's experimentally verified. We can tell this molecule does in fact have a single bond and a triple bond, and the triple is between carbon and nitrogen. And you know what else? I just called it a molecule. It's not. This is a polyatomic ion. So before we're done, we have to finish our picture by wrapping the Lewis structure in square brackets and then putting the charge outside. So if I were to do that a little better so it's more visible, the true Lewis electron dot diagram looks like this with a -1 charge, verified by assigning formal charges. Okay, let's look at another example. Let's do Oh, and by the way, here on your paper, this is the thing we just practiced. If you distribute all the valence electrons and an atom doesn't have an octet, move a non-bonding pair to become a shared pair. Okay, that's going to be the case if there's more than one place to put the double bond, or if one triple bond versus two double bonds is a choice. That's what we just saw here. One triple versus two doubles. Or lastly, if you're not sure the arrangement of atoms, who should go in the middle, who should be on the periphery, formal charge will help you there. Okay, the next one that I want us to do is the nitrate ion. So step 1, add up all the valence electrons. Nitrogen has 5, oxygen has 6, but there's 3 of them, and there's 1 extra electron thrown into the mix. So this is 24 for my target total. Now I'm going to connect them with single bonds. So I'm going to do nitrogen, and oxygen is more electronegative, so I don't want it in the middle. I'm going to put those out on the periphery, and I've just used 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I just hit my target. And all of my oxygens have an octet, but nitrogen does not. 2, 4, 6. Okay, so when we run into that scenario, remember that we move a non-bonding pair to become a shared pair. So I could move this non-bonding pair here. The oxygen still has an octet, but now the nitrogen does. However, it would also have worked if I had chosen to move my non-bonding pair from this spot. So again, here's my 24. Nitrogen is short. I could have moved that non-bonding pair to make a shared pair over here. Or yet another choice. Okay, here's my 24. Okay, the 24 valence electrons, all the oxygens are good, but then nitrogen is not. I could have moved the non-bonding pair from this oxygen down below to create a shared pair. So those are 3 very good possibilities. Now we're going to use formal charge to see if one is better than the other. Okay, I'm going to go through this quickly. Feel free to pause the video if you need to stop and think about it or hear it again. Oxygen has 6 valence electrons. In this picture, it's assigned 2, 4, 6, 7. So that's -1. This oxygen, 6 valence electrons minus 2, 4, 6, 7, -1. Oxygen, 6 valence electrons minus 2, 4, 5, 6, that's 0. Nitrogen has 5 valence electrons minus 1, 2, 3, 4, that's +1. Okay, over here. 6 for oxygen minus 2, 4, 5, 6, that's a 0. Oxygen has 6 minus 2, 4, 6, 7, that's -1. Oxygen has 6 minus 2, 4, 6, 7, that's -1. And nitrogen has 5 minus 1, 2, 3, 4, that's +1. 6 for oxygen minus 7, -1. 6 for oxygen minus 6, 0. 6 for oxygen minus 7, -1. 5 for nitrogen minus 4, +1. Now, let's see what assigning formal charges did here. Do you see that in every Lewis structure, the nitrogen is +1, And out of the 3 oxygens, 2 of them are -1 and 1 is 0. 2 of them are -1 and 1 is 0. 2 of them are -1 and 1 is 0. In this case, assigning formal charge did not indicate that one structure wins over the other. And in fact, the true picture is not really any of them. The true picture is a blend of all 3. That phenomenon is called resonance. Okay, so let's clear up a little bit. This structure is bracketed with a -1 because it's a poly. So is this one, and so is this one. And because any of these 3 gives us the same formal charge assignment, we're going to indicate that the true structure is some kind of blend of all 3. Now, when I say blend, what I mean is that this one double bond, which is shown here or here or down here, is really not in any of those locations. That double bond is delocalized. Okay, so write this down. The double bond is delocalized. That means it's kind of smeared over the whole structure. It is shared in all 3 places. And what we find when we examine a nitrate ion is that all 3 bonds are identical. It's not, oh, there's 2 singles and a double. There's 2 singles and a double. There's 2 singles and a double. No, experimental evidence tells us that there are 3 equal 1 1/3 bonds. I know that's weird. Think of that double bond being shared in 3 locations. That means that this is a little bit longer than a single. It's a single and then a third of that delocalized double bond. 3 equivalent 1 1/3 bonds. Okay. So again, this phenomenon that I'm describing to you is called resonance. It occurs when you have a double bond that could be located in several places, maybe in 2 places or 3 in this case. And when you do the formal charge assignment, you discover that none of the locations wins out over the others. Formal charge assignments are all equivalent. So then we say that the true structure is a blend, and you must represent the different possibilities with these double-headed arrows between them. That's the concept of resonance. So we will do more practice with that in the days to come. That was kind of a lot, but I hope it was helpful. Thank you.